Welcome to the deep dive. Today, we're taking a foundational journey, really getting into proof and abstract mathematics.
Yeah, it's about understanding the sort of grammar of mathematical certainty, how mathematicians build truths that are absolutely solid.
Right. And we're using material from Math 13, an introduction to abstract mathematics at UCI, which sounds like it's designed as a bridge. Yeah.
Exactly. It's meant to take you from maybe more calculation-focused math into the world of abstract thought. Rigorous proof. It's quite a shift.
And the cool thing is, you don't need a deep background in calculus or linear algebra, apparently.
No, not assumed. So it's pretty accessible,
Yeah.
even if your technical background varies. It's about the way of thinking.
So if you've ever wondered why math rules work, or maybe you want a solid base before hitting heavier topics, this should be helpful.
Our mission really is to demystify this core idea of proof and the language that goes with it. Give you a good starting point.
Okay, so let's start right there. Proof. It sounds simple, but in math, it's a very specific, heavy term, isn't it?
Oh, absolutely. Look, in everyday talk, proof can mean, evidence, a good argument, something convincing.
Like in a trial or something.
Right. But in mathematics, a proof is definitive. It's a logical argument that just completely, unequivocally establishes that a statement is true, leaves zero room for doubt.
Wow. So it's not about, like, gathering lots of evidence that points towards something being true, like in science, maybe?
No, not probability. It's aiming for 100% certainty, black and white.
Okay. And these proven statements, they have a name.
We call them theorems. Once something is proven, it becomes a theorem, part of the established knowledge. It's the foundation we build on.
And what about ideas that aren't proven yet?
Those are conjectures, statements we suspect are true, maybe based on patterns, intuition, but lacking that rigorous proof.
So math isn't static. It's about chasing these conjectures.
Very much so. Trying to prove or disprove conjectures, that's where a lot of the action is how new mathematics often gets discovered. It's a creative process.
The notes give a couple examples. Conjecture 1.3. If n is any odd integer, then nn1 is a multiple of 8, in conjecture 1.4. If n is any positive integer, then n plus 41 is prime. How do you even start with those?
Well, often you just play. Try some numbers, see if it holds up for small cases,
Okay, so for the first one, odd integers. n1 gives 0, n3 gives 8, and n5 gives 24. Yeah, those are all multiples of 8.
Looks promising, right? And for the other one, n plus n plus n plus 41, try n1, you get 43 prime, n2 gives 47 prime, n3 gives 53 prime.
Keeps working.
Yeah, you try a few more, maybe up to n of 7, and you get 61, 71, 83, 97, all prime. You start to think, maybe this is always true.
But that's the trap, isn't it? Seeing a pattern in a few cases doesn't mean it holds forever.
Exactly. That is the critical point. To prove something holds for all integers or all odd numbers, you need a general argument. Logic that covers every single possibility.
Not just examples.
Examples can build intuition, suggest ideas, but they never constitute a proof for a universal statement. But they could disprove one.
Ah, right, if you find just one case where it fails.
That's it. Game over for the conjecture. That single failure is called a counterexample. It's incredibly powerful for disproving things claimed to be universally true.
And that's what happens with that prime number conjecture, the n plus 41 1.
It is. It's a famous one because it holds up for a surprisingly long time. Works all the way from n1 up to n39.
Wow, 39 times in a row.
Yep. Seems really solid. But then you hit n40. Let's see. 40 squared is 1600, plus 40 is 1640, plus 41 is 1681. And 1681, turns out it's 41 times 41, so not prime.
Ah, so n40 is the counterexample. Wait, the notes say n41.
Oh, right. Sorry, my mistake. Let's check n41. You get 41 plus 41 plus 41. You can factor out 41, right? So it's 41 plus 1, which is 41, 43.
Definitely not prime.
Definitely not. So n41 is the counterexample. After holding true for so many cases, it fails. One counterexample is all it takes. Conjecture disproven.
It really shows why you need actual proof, not just observation. What about the other one, conjecture 1.3, about not 1 for odd n? Is that true?
That one, as it turns out, is true. But again, the examples we checked aren't enough. We need a formal proof, a logical argument showing it works for any odd n.
Which brings us to actually planning and writing proofs. It's a skill, yeah, not just automatic.
Oh, absolutely a skill. Takes practice. The notes suggest a process. First step, really interpret the statement.
Understand what it's truly claiming.
Exactly. Rephrase it. What are the assumptions? What's the conclusion? What's the logical link supposed to be? Dissect it, basically.
Makes sense. Break it down first. Then what?
Then brainstorm. Try to convince yourself it's true. Why should it be true? Look up definitions, try more examples, maybe edge cases. See if that gives you an idea of strategy.
So explore, play around, build some intuition.
Right. And maybe think about related theorems you already know. Could they help? It's about getting a feel for the problem's landscape.
And to navigate that landscape, we need the right tools, which is where logic comes in.
Precisely. Logic is the language of proof, the rules of the game.
Okay, so what are the building blocks?
Starts with propositions. Simple declarative statements. Things that are definitely true or definitely false. 7 is prime true. Paris is in Spain. False.
Got it. True or false statement.
Then you combine or modify them using logical connectives. And, or, not T, the conditional if-then, and the biconditional if and only if.
And they have those symbols, like the wedge for A and D, the V for or, the little hook for not.
Right.
Yeah.
True implies and for if and only if. Using symbols keeps it precise, and their meanings are nailed down by truth tables.
Truth tables show how the truth of the combined statement depends on the truth of the parts.
Exactly, for every possible combination. So P, A, and D, Q is true only if P and Q are both true. P or RQ is true if at least one of them is true.
Yeah.
Very systematic.
No ambiguity.
None. And from these, you get things like tautologies, statements that are always true, like P or not P,
Right.
and contradictions always false, like P and not P, fundamental logical laws.
Okay. The notes really emphasize the conditional one. P implies Q, Q. Why is it so central to theorems?
Because so many theorems have that structure. If something, the hypothesis P, then something else, the conclusion Q. If N is even, then N squared is even. That's a classic. P implies Q.
And related to P, Q are the converse and contrapositive.
Crucial concepts. The converse is Q, Q. Just flip it. The contrapositive is Q, Chi, P. Negate both parts and flip it.
And the key thing is,
The contrapositive is logically equivalent to the original statement. Peach Q is true if and only if Q, Q is true. They stand or fall together.
but the converse isn't necessarily equivalent.
Nope. If it's raining, P, then the ground is wet. Q is true, but if the ground is wet Q, then it's raining P isn't always true. Maybe sprinklers were on.
Right. The truth table in the notes shows that equivalence with the contrapositive clearly. It also warns about negating conditionals. Negating if P then Q isn't if P then not Q or something.
Correct. That's a common mistake. The negation of peach Q is actually PCQ. It means P su Q and Q is false.
The example was about rain and umbrellas.
Yeah. Negating if it's raining, I take my umbrella. Isn't if it's raining, I don't take my umbrella. It's is raining and I don't take my umbrella. That's the scenario that makes the original if-then statement false.
That makes perfect sense. Okay, so moving on from basic propositions, propositional functions and quantifiers.
Right. A propositional function has variables, like px could be by 5. It's not true or false until you plug in a value for x.
Okay.
Quantifiers. Let's talk about these functions over ranges of values. The universal quantifier, a, means for all. The existential quantifier, a, means there exists.
So ax in the set of integers, x source is 0, 0. That means for all integers x squared is non-negative. True.
Exactly. Or a in the integers such that xos equals 4. There exists an integer x whose square is 4. Also true, x2 or x2.
We can also bound them, like xr, meaning for all real numbers x.
Yep. And a really vital skill is negating these quantified statements. Theorem 2.20 covers this.
It says you flip the quantifier and negate the statement inside. So negating for all x px becomes there exists an x such that not px.
Precisely. The negation of everyone owns a bicycle, x owns a bicycle, is there exists someone who does not own a bicycle, x owns a bicycle.
And vice versa. Negating there exists becomes for all not.
Correct. Negating x and such that sin x equals 4 becomes all x, so 4. And importantly, the domain, like x arrow, stays the same.
Don't change the bounds. The notes also mention trickier cases like hidden quantifiers and implications or multiple quantifiers.
Yes, things like the definition of continuity, eke arrow 0. The order and interaction of quantifiers become really critical there. Needs careful handling.
Okay, so mastering this logical machinery is essential. Now let's talk about the methods of proof. The notes list direct, contrapositive, contradiction, and induction. Let's skip induction for now, maybe tackle that another time.
Sounds good. Induction is a whole topic in itself. Let's focus on the first 3. Direct proof seems like the starting point.
How does it work?
It's the most, direct approach. You want to prove P Q. So you assume P is true. Then you use definitions, logic, other known theorems, step by step, until you deduce that Q must be true.
The example was theorem 2.24. The product of any pair of odd integers is odd. How's a direct proof?
Okay. Assume P, let x and y be any 2 odd integers. By definition, odd means they can be written as x equals 2k plus 1 and y equals 2l plus 1 for some integers k and l.
Right.
Now they want to show their product. Go see. It's awesome. So multiply them out. X equals 2k plus 1, 2l plus 1 wasn't 4k little plus 2k plus 2l plus 1.
Okay.
Look at that expression. You can factor a 2 out of the first three terms. xy equals 2, 2k little plus k plus l plus 1.
Ah.
Since k and l are integers, that whole thing in the parentheses 2k little plus k plus l must also be an integer. Let's call it m. So xy equals 2 meter plus 1.
Which is the definition of an odd number.
Exactly. So we started assuming x and y were odd and directly deduced their product must be odd. That's a direct proof. Q follows from P.
Clean. Logical. So when would you not use a direct proof? When does proof by contrapositive come in?
Sometimes the direct path is just awkward. Or you get stuck. Remember, PQ is equivalent to QCP. So proving the contrapositive is just as good as proving the original.
So you assume the conclusion Q is false,
Right.
QP, and show that must mean the hypothesis P is also false.
That's the strategy. Assume not Q, deduce not P.
The example was theorem 2.26. If the sum of two integers is odd, then they have opposite parity. Why is direct hard here?
Well, if you assume x plus y is odd, say x plus y equals 2k plus 1,
Yeah.
it's not immediately clear how to isolate information about x and y individually. Are they even? Odd, mixed.
Okay, I see. So what's the contrapositive?
Contrapositive is, if two integers do not have opposite parity, meaning they have the same parity, then their sum is not odd, meaning it's even.
Ah, if x and y have the same parity, then x plus y is even. That seems easier to handle.
It is, because
Yeah.
you can break it into cases. Case 1.x and y are both even, so x plus y, y2n, their sum is x plus y plus 2 meters plus 2n plus 2 meters plus n. Clearly even. Case 2.x and y are both odd. So x 2 meters plus 1, y plus 2n plus 1, their sum x plus y includes 2 meters plus 1 plus 2 meters plus 2n or plus 2 meters plus n plus 1. Also clearly even.
So in both cases where they have the same parity, the sum is even.
Correct. Since we proved the contrapositive is true, the original statement must also be true. Sometimes attacking Q or GP is just cleaner.
Clever. Okay, third method, proof by contradiction. This sounds dramatic. Assume it's false and break logic.
Pretty much. You want to prove a statement, let's call it S. You start by assuming the opposite, S, is true.
Assume it's false.
Right. Then you proceed logically from that assumption, S. If you eventually derive a contradiction, something impossible like 0, 1, or P and not P both being true, then your initial assumption must have been wrong.
So the original statement says must be true.
Exactly. The assumption leads to absurdity, therefore the assumption is false.
Example. If 3x plus 5 is even, then 5x plus 2 is odd. How does contradiction work here?
Okay, assume the statement is false. That means we assume the hypothesis is true and the conclusion is false. So assume 3x plus 5 is even, A and D 5x plus 2 is not odd, meaning 5x plus 2 is even.
Okay, got both parts.
Now, work with those. If 3x plus 5 is even, then 3x equals 3x plus 5. That's an even number minus an odd number, which must be odd. So 3x is odd.
If 3x is odd, what does that say about x?
X itself must be odd, because if x were even, 3x would be even.
Okay, so our assumption implies x is odd. Now use the other part.
We also assume 5x plus 2 is even, then 5x equals 5x plus 2. That's an even number minus an even number, which is even, so 5x must be even.
Wait, we deduced x is odd. If x is odd, shouldn't 5x also be odd? Odd times odd is odd.
Exactly. We've deduced that 5x must be even, and 5x must be odd. That's a contradiction.
Yeah.
Impossible.
So the initial assumption that broke the implication must be wrong.
Correct. Therefore, the original statement, if 3x plus 5 is even, then 5x plus 2 is odd, has to be true.
It's like laying a trap for a false assumption. The notes mention one problem proven 3 ways: direct, contrapositive, contradiction. That must be useful for comparison.
Oh, very. Seeing how the logic flows differently in each method for the same result really helps solidify understanding. There's often more than one way to prove something.
The notes also briefly mention using contradiction to prove something doesn't exist, and these helper results called lemmas and corollaries.
Yes, lemmas are like mini theorems you prove along the way to help prove a bigger theorem. Corollaries are results that follow very quickly or easily from a theorem you've just proven. They help structure complex arguments.
We've covered a lot: the meaning of proof, planning proofs, the language of logic, quantifiers, and these key methods, direct, contrapositive, contradiction, feels like a solid foundation.
It really is the bedrock. Understanding this stuff is crucial before you jump into abstract algebra analysis, any of those more advanced areas. It's all built on this.
Maybe listeners could try spotting these logical structures elsewhere, not just math.
That's a great idea. Thinking about assumptions, conclusions, logical steps, It applies broadly.
It makes you wonder, how does this mathematical quest for absolute certainty stack up against how we decide what's true in, say, history or even just everyday life?
That's a deep question. Is there a kind of proof mindset that has wider application? How do we weigh evidence versus logical necessity in different contexts? Something to think about.
Definitely. And as the notes say, this is the launch pad for exploring all sorts of fascinating math fields.
Absolutely. Abstract algebra, analysis, number theory, logic itself,
Hmm.
they all build on these ideas. Hopefully we can dive into some of those specifics in future discussions.
Fantastic. Well, thank you. This has been incredibly illuminating, really getting to the core of mathematical thinking.
My pleasure. It's fundamental stuff.
Until our next deep dive, keep thinking logically.